We can also draw Lewis structures for ions. And we can use Lewis structures to describe why 7 of the elements exist as diatomic elements. Let's look at the diatomic elements. Remember, there are 7 elements that I've asked you to memorize that are diatomic: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. When we try to draw structures for them, we can see why they are so stable as diatomic molecules. Note that when I look at chlorine, and by the way, chlorine, fluorine, bromine, and iodine are all in group 17, so they're all going to have similar Lewis structures. I see that there are 7 valence electrons. There is 1 electron that is unbonded that could be in a bonded situation. If this electron bonds, it would now have an octet. If I have 2 of these near each other, and if I go around finding some chlorine, I'm probably going to find not just 1 chlorine atom, but many of them. So they're near one another. As soon as they come close to one another, it's an ideal bonding situation. They're both high electronegativity elements, so they can form covalent bonds easily. And I see that these 2 unpaired electrons can bond and form a covalent bond, making this nice stable structure of chlorine. So I have 2, 4, 6, 8, 10, 12, 14 electrons, which I should if I have 2 elements with valence of 7. And I have octets on each: 2, 4, 6, 8, 2, 4, 6, 8. So by bonding, they now both have octets, are very stable this way. And it's reasonable that if you find chlorine, you're going to find other chlorines, and all they have to do is come near one another and they will bond. So it makes sense that we're not going to find chlorine like this in its atomic form. We're going to see chlorine like this. Same true is for the other halogens, for fluorine, chlorine, bromine, and iodine, because again, they all have 7 valence electrons. But what about nitrogen and oxygen and hydrogen? Well, hydrogen's really almost the same thing. It has only 1 valence electron, but remember, hydrogen's only trying to seek to get a duet, because a full valence shell for hydrogen, since its N value is 1, it's at the first principal energy level, is only 2. So again, you find 2 hydrogens near one another, they're ideally suited to form a covalent bond, and once they do, they now have complete duets in each one. So this hydrogen has 2, this hydrogen has 2. Overall, we have a total of 2 electrons, which we should for 2 hydrogen atoms, each with a valence of 1. So these are very stable. So this is how we're going to find it in nature, not like this, because as soon as this gets near this, it's going to form this. When we find oxygen and nitrogen, because they're such very electronegative elements, once they come near each other, they can easily grab that other oxygen's unpaired electron and try to form a covalent bond. So we see, however, with oxygen, because it has a valence of 6, it needs 2 electrons, but two bonds. But it's got 2 available bonds for those, so it forms a double bond. Nitrogen has a valence of 5, so it needs 3 more electrons, so it forms a triple bond with another nitrogen. Again, they're high electronegativity elements that want to bond, that are going to be in close proximity to another nitrogen atom or oxygen atom, and can easily form these bonds. So this is the most stable configuration that we're going to find them in. That's why we have our diatomic 7 elements. If I want to make a Lewis structure of polyatomic ion, I can do the same things we've been doing to make them. I just now need to account for that charge. So I would be given a chemical formula with a charge in it of the overall ion. If it's a negative ion, that means that it has gained an electron, or if it's a -2 ion, that has gained 2 electrons. So when I'm counting my total number of electrons and I count up the valence of all atoms, I have to add in 2 or 1 electron for the charge if it's a negative charge. And when I'm done making all bonds, I can place those wherever needed. Now, if I just add them into my total, they just become extra electrons that I can distribute. So in the case of carbon, nitrogen, this would be cyanide ion. So carbon is 4 valence, nitrogen is 5 valence, but this charge is representing an extra electron, so I'm adding that in. So I'd have a total of 10. If I have a positive ion, that means it has lost electrons by whatever the number is equal to the charge. So I can now subtract that amount, whatever the charge is, from my total valence electrons to decide how many electrons I have to distribute amongst the molecule. This is referring to a different method. If I were to first use the valence electrons and to assemble them, I would have to make sure and remove one where I needed to. But we're just going to distribute the total number of electrons where we need them to be using this method. So here's an example. Thiocyanate ion. We haven't introduced the polyatomic ion table, but if we look them up, thiocyanate ion is SCN-1. So this is the structure, this is the formula and charge of it. So I have 6 valence electrons for sulfur, 4 for carbon, 5 for nitrogen, and 1 for the charge, for a total of 16. Carbon is the lowest valence. I'll put that one in the center. I connect with the sulfur and the nitrogen with a single bond, leaving me 2 4 electrons used up and 12 left. I form them on the outer atoms, so I put 2 4 6 here, 8 10 12. I've run out. So at this point I have the 16 electrons total, but I need to rearrange them because carbon currently only has 4 electrons. It does not have an octet. So I have a couple of options, and we already evaluated this options in the formal charge, but we can see how I would have come up with these 3. At this point I say I could take this lone pair and make a double bond, or I could take this lone pair and make a double bond, or I could make a triple bond with one of them. I could take this one and this one, 2 of these, and make a triple bond with the nitrogen, or I could take 2 of these and make a triple bond with the sulfur. So I have a couple of options here. And we evaluate these 3 options in the formal charge video. So for your job, I want you to try to draw the structure of sulfate ion. So this is a SO4 molecule with a -2 charge. Determine the total number of electrons and then follow the same steps as you would for a neutral molecule Lewis structure.